So we already looked at Raoult's law in the previous video, and we looked at a case where we had a binary solution with a volatile solvent and a non-volatile solute, and then we said that the vapor pressure of the solution of the volatile solvent is going to be directly proportional to its mole fraction in the solution. So now we look at what happens when you have two or more volatile components in the solution. For example, if you had two or more liquids mixing with each other. Let's consider a binary solution with two liquids. Let's say you have liquid A and liquid B. And whichever is in the largest quantity will become the solvent, and the other liquid is a solute. But in any case, so you can extend the Raoult's law to this case as well, and you can say that the partial vapor pressure of liquid A is going to be, let's say PA, is going to be again directly proportional to the mole fraction of that liquid in the solution. And then partial vapor pressure of B is going to be directly proportional to the its mole fraction in the solution. So in case of a binary solution, your XA plus XB should be equal to 1. And if we rewrite these proportionality relationships here using a proportionality constant, you can say PA equals XA times the vapor pressure of this liquid in its pure form when it's not as part of a solution, it's just a pure liquid. And then similarly you have PB equals XB times PB naught or PB0, which is again its vapor pressure in its pure form. So that is pretty straightforward. It's just an extension of what we did earlier. So now we also know that from our previous So if you want to look at the total vapor pressure coming from the solution in the space above the liquid surface, the solution surface, you will call that P total. And remember, this is just P total coming from the vapor pressures of the liquids in the solution. So P total is PA plus PB. You can possibly have some other gases in the air. I mean, you could actually have a closed container with these two liquids in it, but in the space above the liquid surface, if you already had air to begin with, that is going to add to the pressure. When you calculate the total pressure above the liquid surface. So this P total is just coming from the vapor pressures generated by the solution, and it doesn't take into account the pressure of any gases or any air that is already present in the container, if at all it is present in the container to begin with. So here, if you just consider PA plus PB, you can rewrite this as XA PA 0 plus XB times PB 0. And then we know that since it's a binary solution, you can actually write this as plus 1 minus So since this is a binary solution, you can rewrite this as XA times PA 0 plus 1 minus XA times PB naught or PB 0. So that, again, rearranging the terms here, you can say XA times PA naught minus PB naught plus PB naught. Or if you actually substituted XA with 1 minus XB, then you will have XB times PB naught minus PA naught plus PA naught. So you can write either ways. I mean, either ways, it's the same thing. All we are trying to say here is the P total, that is the total pressure arising out of the partial vapor pressures from the volatile components in the solution, can be written as a as a function of the of the mole fraction of any one component. So the only variable here is the mole fraction. Everything else is a constant, because we know at a particular temperature the equilibrium vapor pressures of a pure solvent, of a pure liquid, is going to be a single value, and that is a constant. So that's why you have these PA dot naughts or PH zeros or PB zeros. So the only variable here is XA and XB, if at all. And so it is a function of the mole fraction of any one particular component, either XB or XA. It is, so P total can be written as a function of either mole fraction of component A or mole fraction of component B, and that's all it means. So if you were to draw a graph vapor pressure versus, let's say this is going from XA equals 0 here and XA equals 1 and XB equals 1 here and XB equals 0 here. So in this case your PA might look something like this, partial pressure, vapor pressure of A, component A, and in which case this will be at XA equals 1, this will be PA 0, and your PB will look something like that. Let's say in this case, let's say PB naught is a higher vapor pressure in the pure liquid form. So if you actually join these two, this is going to be your P total. So it's a simple calculation that so it's a simple calculation that comes out of rewriting this Raoult's law.